All right, hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. We found some bugs yesterday, and we fixed some of those bugs yesterday, as well as doing some optimization work. But we had a bug that we needed to leave till today because I think it's going to be a relatively involved one math-wise. And so, normally I would say 10 years ago. Well, let's say 15 years ago. Nah, 10 years ago would have been fine. 10 years ago, I think this is the kind of math problem that I wouldn't think about very long. I just feel like, oh, here it is. But since I've been spending my time for the past, God, I don't even know how long, not doing these kinds of math problems, I'm often a little bit rusty at them. So I feel like this is, I just felt like it was likely. It was likely to take some time to work it out due to the rustiness of it. I gotta figure out, I wonder why Milton always loses the ability to capture the tablet when it's been open for a while. Nobody seems to know why. Someday I should go debug it. We have the source code, but I don't know why. And neither does anybody else. So anyway, point being, let's take a look here. Here we are on day 319. And this is for, skew UVs. I should actually say skew UV mapping, maybe. And for those of you who don't know what I'm talking about, because maybe you didn't see yesterday's stream, we wrote a thing that, like a quadrilateral mapping routine when we originally wrote the renderer for this game. Because remember, we don't require OpenGL at the moment. We actually can just render the game entirely in software ourselves. And so what was going on there was we wrote a mapping routine where you could give it a y-axis and an x-axis, and you could rotate those however you wanted, and you could scale those however you wanted, and it would warp the image. So, you could map an image on, you could do something more like this if you wanted to, and it would, stretch the image out, right? So a standard texture mapper basically that worked with a quadrilateral. The quadrilateral has to be, a parallelogram. So not a rhombus, but an actual. It always has two sides, both sides parallel, and that all worked fine. And we got that working, and it was fine. But we never really supported the ability to skew. So stuff like this, if you were to actually construct using a real parallelogram, not a rectangle, not a rotated rectangle, but an actual parallelogram, where this, is not 90 degrees, this is some other angle here that is not 90. This is not 90. We don't really support that. And the reason that we don't support that is because I kind of took a shortcut in how I did the UV mapping of the quadrilateral, and so I just wanted to take this opportunity to describe what that shortcut was. We probably described it at the time, but we probably didn't dwell on it very much because we weren't really thinking about the skewness of it at all, and so on and so forth. So maybe let's just take a minute to kind of talk about what was going on in this situation. So first, let's talk about, and I'll try to not make too many math mistakes, but like I said, I'm a bit rusty at these, so you're going to have to bear with me on that. Conceptually speaking, I just want to say here's what we're actually doing. Okay, so we have, if you would imagine, this is our texture. And on this texture, we've got, some pixels or whatever, and essentially you could think of this, if you want to think of it conceptually, you could think of any point on this thing. We could think of this as being defined by all these points. If you don't even think of it as a texture map, just think of it as a space in where there's a bunch of colored points, right? Because we're talking about a transform. We want to think about the transform. So pixels, we don't care about pixels right now. We're not even thinking about pixels. Let's just think about points, right, that are on this texture map. And the point could be anywhere. It could be over here, it could be in here, it could be on the surface, whatever. Any point in this texture map, right? So what we know is that we've got these basis vectors here, right? that define this, and these are the x and y basis vectors of the texture. And then what we're doing when we do a texture map, conceptually speaking, even if this isn't how we're actually computing it, is we're taking these and we're sort of specifying where those go on the screen, right? So let's take the case of when I was still using rectangular rotated rectangles, rotated scaled rectangles. We have a y-axis and an x-axis, right? And those correspond here. So we're essentially taking points and we're transforming them over here. So if we wanted to, and we should also point out there's also an origin, right? So there's some kind of a basis point here that we're talking about. And so I don't know what we'll call that. Let's just call that, I don't know, we'll call that A. So all right. So if we have a point here, a point P, what we want to know if we're talking about the forward transform. So I'm talking about if I actually had a bunch of points and wanted to transform them into the space, right? So if I'm talking about the forward transform, which obviously doesn't help us at all in this particular circumstance, but trust me, it matters why we want to think about it that way for a second. What we're basically asking for is how to create a P prime over here that's in the same place as the texture would be if the whole texture was kind of warped, and moved and warped over to the location that we want the texture to be on the screen, right? So, P prime is our screen position, and P is the texel space position, right? And so we could talk about this transform. And maybe A was a poor choice here because I probably would use a large A for it, but I don't know. We'll sort of creatively turn that into a B. Let's say we've got an A here, so I'm just going to describe this transform A that's going to take these points and do the operation that I want to do, right? So assuming that this is how I'm going to conceptualize it, what I'm saying is that if I was to multiply, if I was to perform the transform A on the point P, I would get back that P prime, right? And so this is a very straightforward sort of matrix statement I would be making. I'm saying that I have a transform that is the transform that moves from texture space. That's where this is at 0, 0. That's where this is at 1, 0, and this is at 0, 1. Right? This like known space. And it moves everything over to this other space here where the origin is not at 0, 0, it's at B. And these vectors are not 0, 1, and 1, 0. They're some random vectors that are whatever they are. They could be anything, right? So let's talk about that shortcut that I took given this matrix equation, the most simple kind of matrix equation you can really ever have. Let's talk about what this actually looked like. Now, I know that some people's eyes gloss over when you see matrices, and so I always like to just remind everyone that really we're just talking about bags of numbers here. This is a 2D transform. Let's take a look at what this actually looks like if we talk about it specifically, right? So what's this P prime here, right? Well, this P prime is this right here. That's just the x and y coordinates of the point in screen space, right? So that's literally just like the screen x and the screen y. That's all we're talking about for this P prime vector. We then have some matrix A, right? And who knows what that matrix A is. We're going to talk about that in a second. And then we've got this vector P here. And what's the vector P? Well, that's the u and v coordinate, right? That's like whatever the UV coordinate was to get that point of the texture map, right? So I don't know what it is here, 0.8, 0.8, something like that, kind of, it looks like maybe, or 0.9, 0.9, who knows, right? And so the question is just, what is this A, right? What is this A vector here, right? And so in order to actually do the origin transform with the B, we could, you've seen matrices where we extend to homogeneous coordinates and include the translation in the matrix and all that stuff. We're not going to look at that at all. So what I'm going to say is I'm going to say that we just have the B is a separate origin shifting term out here, right? I'm just going to say that, we don't care about that. That's just, whatever this screen space origin is here, wherever we wanted it, is this other term. Because we don't care about that at all, right? We can trivially, to perform the reverse mapping, which is the thing that we actually care about, or the forward map for that matter, we can always just subtract away this origin and get just the vector p prime, and this then becomes the same 0, 0, right? So translating this back to the origin is trivial, and I don't want to complicate the matrices for you, thinking about the homogeneous nature of them and that other stuff, because that's really graphics trickery. It's not really that important, and not something we need to concern ourselves with for this problem at all. So let's take that out of the equation, pun intended, and just focus on the actual part we care about, which is the actual transform of the shape, right? So that skewing, stretching transform, which is a 2x2 transform on the u and v that bends it into this shape that it's in, okay? So let's think about what has to happen there, right? Well, I've got an sx and an sy, and what I want to do is I want to interpret them. Remember, sx was interpreted this way originally, right? Oh, I'm sorry. I don't mean that. I meant uv. Got a little ahead of myself there. So that u, right, is interpreted this way, and that v is interpreted this way, right? So essentially, here is the v, here is the u, okay? So if I wanted to reproduce this point over here, then what I was thinking to myself, right, is I was thinking to myself, well, okay, if I want to go, you know, however far I need to come this way for my u coordinate, and however far I need to come this way for my v coordinate, well, then clearly the x vector, you know, whatever this x vector is here, that is just the columnar component of this guy. So, you know, I've got xx, xy, whatever that's this vector here, right? And I've got yx, yy as, you know, and that's this axis here. That's all I need. Now, why did I think that was true, right? Well, look at what happens if I'm actually going to, if you actually multiply these out, right? I taught you how to do matrix multiplication, so even if you don't know before Handmade Hero, you should know now. If not, where were you when we covered this? We've done it multiple times now. So remember, if I multiply this out, you'll see what I get. Remember, you think of it this way. You take the first element in the row and the first element in the column, you multiply them together. So it's uxx, right? Then you take the next element, and multiply those together as a sum. So vyx, right? I do the same thing here. So I do uxy, and I do vyy. I wish u and v were a little more clean, right? And this is the result I get, right? It's a vector result, right? There's two elements to it, this one and this one. And if you look at how these break down, you can see these terms isolate very, very cleanly, don't they, right? I could rewrite this by just cleaving it at the plus line, and this is clearly u times xx, xy plus v times vyx, vyy. Okay? Now, what are these two? Oops, I doubled my v there for no reason. There we go. Yx, yy. Right? And this is just the x-axis. This is the y-axis of my transform up there. So it's just ux plus vy, right? And that's exactly what I said I wanted. I wanted to go out the x-axis by u, and I wanted to go up the y-axis by y. That's what I was trying to do, right? So that is why I constructed in my head when we were doing this. That is why I was thinking this way, right? So my A matrix, I know what it is. It's exactly what I just said, right? It's exactly this. But this is not an operation that we ever actually do, right? It's just not an operation we do. We never have to, in Handmade Hero, at the moment anyway, we never have to take a point in texture space and map it onto the screen. Because remember, the way we do our texture mapping is we just loop over the pixels and we try to figure out where in the texture map each pixel came from. So we actually don't want A, we want the inverse of A, right? We want to do the backward transform. That's what we were doing. Okay? So how did I write that backward transform, right? What did I actually type in as the code? Well, if you remember, what I typed in is from the SXSY here, and I'm going to go ahead and eliminate B entirely. We're just not going to, like I said, we're not going to talk about, we're going to pretend we already subtracted B out. So pretend this is the entirety of our equation. It's just SXXY times, equals the matrix times the UV, right? So what did I type in? Well, I typed in two dot products. I don't know if you remember this, right? But the dot products I typed in were, if we, let's call this the, the S vector. Well, I guess we called it P prime, so that's fine. The dot products I typed in were, I wanted to take P prime transpose X, so I wanted to dot product this and this together, right? That was going to be my U coordinate, and I said I was going to take the same thing with the Y axis, and that was going to be my V coordinate, right? That's what I said. Now, why did I say that? I might have explained it at the time. I don't know if I did or if I didn't, but I hope I did. But now let me just explain it again, because it's crucial to understand where I got that before you can really understand what the bug is. Okay? So where does this come from? Where does this concept come from? Well, remember, we have our matrix equation, P prime equals AP. Okay? And we know that that is SXSY equals XX, XY, YX, YY times UV. Now, I want to solve this equation. What I want to do is I want to get the U and the V, right? That's what we need to look up into the texture. But I only have the SX and the SY, right? So effectively what I have to do is solve this equation for P in order to actually produce the UVs that I want. So what that, involves is multiplying by the inverse of this A matrix, right? If I have P prime equals AP, well, if I want to solve this equation, I need to multiply both sides on the left by A inverse P prime equals A inverse AP, and any matrix times its inverse, obviously, is going to equal the identity matrix, right? So that goes away, and I get A inverse P prime equals P. Okay? And so since what I'm trying to solve for is the P, it means that the thing that I'm trying to compute is A inverse P prime. That's what I want, right? So I want, moving back up to here, if what I want is A inverse P prime, well, that means I've got this XX, XY, YX, YY matrix that I have to invert somehow. And we haven't really talked much about how to invert a matrix, right? So we have to be able to invert a matrix. That's one thing we have to do. And then we have to take this and multiply it by the input, the SXXY, right? That's what we have to do. So I never inverted this matrix, right? Inverting the matrix is not in the code, and I don't know if we talked about inverting the matrix or not, or what happened, but that never happened. So how did I get from wanting to do this equation to computing this, right? How did I get there? Because it's kind of close, right? I mean, this is P prime here, right? And it does produce the U and the V, and the X and Y axes are there. But how did I get there? Well, the answer is I kind of used a little bit of a trick, just mentally, without probably going into too much detail of it. That is, if you want to invert a matrix, if you know some things about the matrix, you can take a shortcut. There's a number of things that you can do. What are those shortcuts? Well, let's start with a very simple one. Let's suppose that you have an orthonormal matrix. Or rather that the vectors in the matrix, XX and YY, were orthonormal. What does that mean? Well, an orthonormal pair of vectors is a pair of vectors that meet at 90 degrees, right? And are also unit length. So this is, one long, and this is also one long. Okay? If you know that you have if you have two orthonormal matrices, two orthonormal vectors, so say that x and y were orthonormal to each other, then inverting your matrix is as simple as rearranging the terms. You don't even really have to do any work to invert the matrix. If I have an orthonormal matrix that looks like ax, ay, bx, by, like this, right? And I know that A is A and B are orthonormal, right? So I have this, I know they're orthonormal. Then the inverse of this just equals the transpose. And the transpose just means flipping everything around the diagonal, right? It's ax, ay, bx, by, right? So you can see the ax and the by stay in the same place, but the ay, bx, they swap, right? Now, it's a little confusing. It's like, why does that happen, right? It's like, it's one thing for me to kind of sit here being mathy about it and saying like, hey, guess what, guys? The inverse in this case happens to equal this. So really, you could say that A inverse equals A transpose, right? In the case where the vectors that make it up happen to be orthogonal, right? But why is that true? Give some geometric intuition to why that's true, or some algebraic intuition or whatever. Well, I can probably give you both. My linear algebra skills aren't so rusty that I can't probably demonstrate that in both ways, actually. So let's start with the algebraic way, and I'll show you the geometric way second. So what actually do I know about inverses, right? What is an inverse of a matrix? Well, you could think about inverses of matrices very much like inverses of anything else, right? It's the opposite operation. And it's the thing that is the unitary inverse in this case. So for example, to map it back to something that you may be more familiar with if you're not too comfortable with matrices, let's say that we just took a number. Like, let's say we took the number a equals 5. Right? So it's just a symbol a, it equals 5. If I wanted the unitary inverse of this, right? If I wanted to, the multiplicative inverse, if you will, right? If I wanted to say what multiplied by a gives me 1, right? So I have some number, I want something that I'm going to call a inverse. I'm going to multiply it by a, and I want it to equal 1, right? That's what I want to have happen. Well, you can find out pretty trivially what this is, right? You have an equation in only one unknown, a inverse, right? And I have a known value for a, which is 5. So if I have a inverse 5 equals 1, well then a inverse is pretty obviously 1/5, right? And that's exactly what you know intuitively. You know if I give you the number 5, you know that 1/5 is the thing you would multiply it by to reduce it back to 1, right? And so for any, a, 1/a is always the multiplicative inverse of it. You can always take anything, well, if that thing is not 0, you can always take anything and, invert it like that, and you get something that will multiply out to 1. So the inverse of a matrix is a very similar concept. There's just a lot more to it because there's just so much more involved, right? But it's very similar. It's the thing that I multiply a matrix by in order to produce the identity, in order to produce a value which when you multiply by it, it does nothing, right? Because that's what this was, right? This was a way of producing 1, which is the value that does nothing when multiplied, right? It is literally an ineffectual multiplier, right? And that's the same concept for inverting a matrix. When I do a matrix inverse times itself, when I do A inverse times A, I get the identity matrix. The identity matrix is just like 1. It's the thing that you can multiply other matrices by, and it does not affect them. It's a pass-through, right? And it actually looks, like this, right? It's just a, ones down the diagonal the whole way, right? And so anything that you multiply by, it just produces a copy on the other side, right? It does nothing. So it's exactly like 1 for multiplication. It's just this is for matrices. So hopefully you're comfortable enough just with conceptually what that means. A inverse A equals the identity matrix. Well, now I can tell you algebraically why that inverse transpose, why this is true for orthonormal vectors, right? And so let's say we just do out exactly what I am suggesting we do here. Let's say that we pretend that A inverse equals A transpose, and I have these vectors that are orthonormal, right? So I start with AX, AY, BX, BY, okay? That's the matrix. And I'm going to reproduce exactly this equation that I wrote, right? A inverse A equals the identity matrix. Okay. So if I were to take the transpose of this matrix, which I just told you how to do, right? This is A up here. This is going to be A transpose right here, right? Which I'm saying equals the inverse. I know that my AX and my BY stay in the same place. I know that my BX and my AY switch, right? Well, let's multiply these matrices together. We know we're going to get another 4x4, I'm sorry, another 2x2 matrix, another 4-element matrix. We know how we do, right? We know how to multiply. We've done this a bunch of times on Handmade Hero. So it's going to be AX squared, right? AX times AX, AY times AY, right? So it's like AX squared, AY squared, right? That's what that's going to be. Then here we're going to get AX BX plus AY BY, right? AX BX, AY BY. Down here we're going to get kind of the opposite of that, right? We're going to get AX BX plus AY BY. Oops. Did I write that correctly? Yeah. AX BX, AY BY, right? And you can see how it's kind of like producing the exact same terms here, right? And then the same thing that happened up here to this vector, which is squaring itself essentially, is going to happen to these down here, right? So I get bx squared plus by squared, right? So this looks like a bunch of gobbledygook, right? It's like, what's going on here? Like, I thought you were going to tell me how this equals the identity matrix. I don't understand. Well, if you actually look closer at what these things are, you can very quickly see why it actually is the identity matrix. And here's why. Well, what is AX BX plus AY BY, right? What is that? It's the dot product of A and B. That's A transpose B, right? Remember A transpose B? AX times BX plus AY times BY. It's the dot product, right? Same thing up here. That's just A transpose B. What's AX AX plus AY AY? Well, that's A transpose A. And what's BX BX plus BY BY? Well, that's B transpose B. So actually, the matrix that I produced is A transpose A transpose B transpose B, and A transpose B again. These are equivalent terms. Well, what are those values? I would invite you to look back here at A and B are orthonormal. And what did I say? What did I say orthonormal meant? I said it meant they had unit length and that they met at a right angle. Okay, do you see it yet? If not, I'll keep going. A transpose A, you know the dot product. I want everyone on Handmade Hero, you better know the dot product. I've said it so many times. You know the dot product of A times A. It's the length of A times the length of A times the cosine of the angle between them, right? B times B, length of B times length of B times the cosine of the angle between them, right? A transpose B, last term, length of A, length of B, cosine of the angle between them. Well, tell me now, what are all these lengths? I just said everything has a length of 1, right? So all of these terms go away. They're gone because they're all equal to 1. So all we have left is the cosine of the angle between them. Well, what's the cosine of the angle between two vectors that are the same vector, right? That's an angle of 0 and a cosine of 1, which means A transpose A and B transpose B are both equal to 1. Hey, guess what? 1, 1. A transpose B, what's the cosine of two things that are 90 degrees apart? What's the cosine of that? Well, it's 0, right? The cosine is 0 when it gets to 90 degrees. 0, 0. That's exactly what I wanted, right? 1, 0, 0, 1. So effectively, you can think of this, and if you go down the linear algebra path, this is, this is real basic linear algebra. This is day one linear algebra stuff that I'm doing here. But if you've never done matrices, obviously I think it helps to kind of ease into it, obviously. But you can always think of matrices as just a giant bag of dot products, right? It's just dot product of this, this vector dotted with that vector is this entry, right? So each entry, you can think of a matrix multiply as taking all the possible dot product combinations that you can make from two incoming matrices, and each element of the corresponding matrix is a different combination of dot products, right? So that is a really easy algebraic way, right, of seeing why the inverse is the transpose, because when you happen to know that these are orthonormal, all the math just comes out, right? When you actually do that multiplication, it's like, oh, look, everything on the diagonal happens to be a dot product of a vector with itself, and all of them are length 1. And everything on the other diagonal happens to be a dot product of two vectors that are 90 degrees apart, right? And so to put it in sort of meta-algebraic terms, if, like I said, if you start to think of these as just a series of vectors, right? Then what you can think of is if I was to start with some vectors up here, A, B, C, D, who knows? So 4 vectors, each 4 long. And I transpose them, A, B, C, D, right? Then you can just think of the diagonal of the matrix just being all the dot products of things with themselves, right? B transpose B, C transpose C, D transpose D, all the way down however big you made this matrix, I don't care. And then all the off elements are all the dot products of some vector with some other vector. So the reason that, conceptually speaking, any matrix times its transpose will give you the identity if you know that all of the vectors in it are orthonormal, all of the columns of it are orthonormal, all the rows of it are orthonormal, whichever way you want to think of it, right? Is because you then know that all of the diagonals will become 1, because you're always taking the dot product of a unit length vector with itself, and that's always 1. And everything off the diagonal is always going to be the dot product of some vector with some vector that's 90 degrees apart from it. So it actually doesn't even matter at that point what their lengths are. Their length could be anything, but the cosine term will always be 0. So everything off the diagonal becomes 0. And the only thing you get when you have 1s down the diagonal and 0s everywhere else is the identity matrix. So conceptually, algebraically, I hope that makes some clear sense as to why this is true, right? So now let's look at geometrically why it's true, because some people like to think in geometric terms, some people like to think in algebraic terms, some people like to think both. Usually being able to do both is usually best, because some things work well algebraic, some things work well geometrically. It's handy sometimes to be able to switch back and forth between them when something's not working. But let's talk about the geometric construction of this, right? So like I said sort of previously, we could think of one of these vectors, one of these matrices, and I guess let me write it out: ax, ay, bx, by. We could think of one of these matrices like A, and I want to sort of have something, a vector here that I can multiply by it so that I can show something algebraically, right? In fact, I don't even really have to do it again because I suppose I already did it. Well, I'll just rewrite it again. It's easy enough to rewrite, right? It's uax plus vbx, uay plus vby, right? And so what I said was, well, you can see very clearly that that's u times a plus v times b, right? So geometrically, we've talked about this many, 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 many times, right? All that's doing is saying, well, all right, if you imagine that I had some perfect space over here where I had, u and v like this to get to a point, and there's my vector uv, right? If I then take some other, basis here, which is my ax, so here's my a and here's my b, I can then just reinterpret these, right? I can say I want to go this far along in u, and I want to go that far along in v, and I get to that point, right? And that's the forward transform of this thing, right? We've done this so many times. You just go u along the a vector and then v along the b vector, and you get to the point. And that's how you do a basic transform, right? Well, if you think about what the inverse of this is, right? So I want to do the inverse operation geometrically. I don't want to go this way. I want to go that way, right? Well, what would I do? Instead of u times a plus v times b, I want to do the opposite. I want to dot product, right? I want to project. So I want to take this and project it onto the a. So I want to take whatever this vector is. What am I going to call this vector? I guess we'll call this vector p, because I have nothing better to call it, right? So if this is my point p here, I want to dot product it with a to produce u, right? I want to drop that perpendicular down to produce the u value. And then I want to dot product it with b for the same reason, to produce that v value. Well, how do I produce a dot product with a and with b, right? It's exactly what I just said. If these are going, in the column order, if I was to transpose them, so it's ax, ay, bx, by, right? If I take that transpose, now they're lined up such that multiplying by the matrix does the dot product. There it is right there, right? So now, instead of computing the thing that moves you out along the vectors, conceptually speaking, which is this, I produce the thing that dot products with those vectors, which is the measurement version, right? So again, you can see, conceptually speaking, if you want to think about it geometrically, you can just think about it as going the transpose, if everything's orthonormal, the transpose takes you from vectors you move along, and it instead of multiplying by those vectors, your two coordinates, it makes it so that now you're dot producting against them, right? And that's the difference between thinking of a matrix in column form and thinking of it in row form, right? If I have a matrix that looks like this to me, and once you're into linear algebra, you just think this way usually. If I have a matrix that looks like this, I think, this is a forward transform matrix, because it's been labeled such that the common terms are going down, right? So I know that when I multiply by something, I'm producing a series of vector products. Whatever I put here, I'm effectively multiplying by, that column, right? And then I'm adding the next column times something. Right? So when I see columns of coherent values going down a matrix, I know this is effectively something that when multiplied by a vector, you will basically be producing a series of scaled, summed vectors, right? Those column vectors, these are effectively the scales that scale each column of the vector, right? But if I see it the other way round, if I see it labeled like this, now I know what we're doing is we're measuring, right? We're taking the dot product of something against it, right? It's the same operation, same multiplication. It's just what values did I put in it? That determines what I get out, right? Same, matrix math is matrix math, but the values I put in and how I've arranged them in the matrix determine what I'm computing, obviously. And so you can kind of see that if I'm thinking rows or thinking columns, thinking columns or thinking rows, that depends on what this matrix does conceptually. So hopefully that gives you enough of an understanding of why, if we go all the way back here, scroll through the blackboard, of why I wrote this. Because what I did is I just transposed the matrix, conceptually speaking. I wanted to go backwards, so I transposed the matrix. But all of that stuff I just explained to you now, you can see that only works if these things are orthonormal. Now, I knew they wouldn't be orthonormal because we tested scaling, right? So when we tested this thing, if you remember, we tried making things bigger or non-uniform scaling, but we kept this angle at 90 degrees, right? So what does that do to our matrix, right? If I've got an AX, AY, BX, BY matrix, right? And I know these things are scaled, right? So I know that A has a scale on it. We'll call that, I don't even know. I hate having to make up letter names for things. I'm like so bad at it. But anyway, so let's call that M. And we'll call this one N, right? So now I've taken these vectors, and instead of them being orthonormal, they're still at 90 degrees to each other. They're still orthogonal vectors, but they are not orthonormal vectors anymore. And the reason is because A is M long, and B is N long, and M is not equal to, 1, and N is not equal to 1. They're something else, right? So now what happens to our fundamental... By the way, I hope everyone was interested in the matrix thing today, because apparently that's all we're going to do. I don't know. Sometimes I get into it, and it's just we're into it at this point. So anyway, what does that do to the fundamental operations we were trying to do before? Okay. Now you can see immediately why this works for the forward case, because all this M and the N do is they just multiply our U and V out, which is what we wanted, right? It just makes it go further. Okay, because what I get is MUAX and plus NVBX, MUAY plus NVBY, right? All I've done is just increased the distance I moved along my vectors. Instead of going UA plus VB, I am now going MUA plus MVB. That's it, right? So the forward transform works great. Now let's see what happens if I transpose this matrix. Does it work for me again, right? Does it just magically work? Well, what would I get if I transfer this matrix? Well, I have MAX, right? But now down here I actually have NBX, right? And then up here I have my MAY, and here I have my NBY, right? You can see that's just, I swapped these two, right? So now when I do my dot product, right? So I'm going to dot product this with something. Now when I do my dot product, I have a problem. There's a problem here. We know the length of the A vector is 1 if it's just A, but when it's been scaled by M, now the length is M. So previously, when I was doing stuff like A transpose P, right, which is what this was producing for me before, right? If I had my point I was trying to measure here, and I multiply this out, right? Now, instead of A transpose P, I've got M A transpose P, right? This is the value I want, a unit length A transposed with my P, but there's this multiple in there, and I don't want that, right? So how did I compensate for that in the code? Do you remember? What I did is I baked out the M, effectively, right? I took and I looked at what the length of A was ahead of time, and then I divided it by that number, right, to get it down to be orthonormal again, right? I basically made it back into a unit length vector, if that makes sense. So I hacked in some code. I didn't really hack it in, but I mean, I mentally knew that I could compensate for just the scale and still use the same trick by effectively turning the things into orthonormal vectors, if that makes sense. So yeah, so that was what was going on there. And similarly, I think we, I'm trying to think of exactly how we ended up doing that, but I think we used the fact that it was squared to do a division. I don't really remember exactly what we did, but point being, that is why it was working for scaled, is because I took advantage of the fact that we could effectively think about this where the scale was separate and still do the same trick. Now, for those of you that want a little hint of linear algebra, like a little bit, or why, you know, what that would look like if you were being more formal, what you could think of it as is if I have an A matrix and I want this A matrix to be orthonormal, right? Because I want to be able, you know, I've got something like this and I want to be able to do this, right? And when I do that, I want to be able to do a transpose. Well, if I've got a matrix that's just, it would be orthonormal except the vectors in it happen to be scaled, then what I could do is think of that as two separate matrices. I could think of that as SAP equals P prime, where S is a scaling matrix and A is an orthogonal matrix, an orthonormal matrix, where all the vectors are orthonormal, right? So A is our original matrix and S is just a matrix that has the scales in it. So if we had here, like we were up there, we had the M and the N, right? Then if you look at what happens to a matrix that looks like this, where it's a diagonal matrix with just numbers on the diagonal, that acts as something that will scale other matrices, right? Or vectors. That's a scaling matrix. Why does it do that? Well, you can kind of see if I just write it out, if I've got, you know, my matrix here, A, without the scale in it, well, what do I produce here? Well, A times M is obviously MAX, right? AY times 0 is nothing, so there's no extra term, right? Similarly, BX times M here, wait, is that right? That's not correct. This has to be on the other side. Yeah, I think I've got this backwards. In fact, I do. Okay, so like I said, try not to make too many math mistakes. I don't know that I made any yet, but that one was one. So SA, AS. Might as well explain everything since we're here. So why did I just have to back that up? All right, so far we've mostly talked about matrices transforming things singularly. Well, when you do matrix multiplication, it's actually order dependent. And, you know, that's, I guess, one of the main things that sort of separates it conceptually from regular multiplication when you think about working with it. You know, if I have A times B and A and B are both numbers, you know, it's like 5 and 4 or whatever, B times A is the same thing, right? So I can commute the terms in multiplication and it doesn't matter. I can move them all around. In matrix math, sometimes that's the case. Sometimes it may be that two matrices can be swapped and their product will be the same, but in general it's not. When you have two matrices, because the multiplication happens by columns on the second, it's by columns on this guy and by rows on the first guy, right? I mean, you saw me do this multiple times, right? I kind of line them up and I do it like this. Because of that, it matters who's in which slot, right? For diagonal matrices, it doesn't matter because you're always going to produce the same terms on the diagonal. They're always going to just pick out the exact same things. But for all the off-diagonal elements, it will differ potentially depending on the structure of the matrices, right? So actually, these two things are different. If I scale here or scale here, I get a different result. And if you've ever worked with 3D graphics before, even if you didn't understand matrices that well, you kind of have found this to be true of transforms. If you've looked at an equation like this, where I do ASP, the scale happens to P first and then the rotation of A. Whereas the other way round happens here. First P is rotated by A, then it is scaled, right? And those are two very different geometric operations, if you think about it, right? If I was to take and start with a point P, right? And I was to apply a scale to that point, right? You know, maybe out to here or something like this. And then I was to rotate the point around, if that makes sense, right? I might get a very different result if the scale is non-uniform, right? If the scale was uniform, which I guess I kind of drew, so I should draw a non-uniform scale. So let's say I'm going to scale along this axis and only this axis, right? So the scale is very non-uniform. If I do that and then rotate, I'm going to get something very different than if I rotate and then do that scale, right? So if I was to have a scale that was I'm out of time. Darn, son. All right, well, anyway. So that actually is captured by the matrix math. And you were about to see it happen there, so I'm going to do it again for you now that I've explained what's going to happen so it's not going to be too confusing, right? So let's say I have my scale matrix M this time, 2 M's, and then my, my A matrix, right? Well, now I'm okay. I get MAX, MBX, and I get MAY, MBY, right? That was equivalent to the thing I was about to draw there, which is like, hey, if I just scale everything uniformly, then the point ends up in the same place. Because it doesn't matter whether I rotate first and then scale, or scale first and then rotate, because they'll put me in the same place. That is captured by the matrix math, and you can see it, since the M's will multiply everybody the same. It doesn't matter where I was. I could flip these two guys around, right? Do the exact same operation. In the reverse order, doesn't matter, right? I still just get MAX, MBX, MAY, MBY, right? Still the exact same thing. But if I actually wanted to reproduce the thing I was talking about with a nonlinear scale, right? So when there's M and N, I can't do that anymore. If I try to do it at the head end, right? Then I end up with the problem I had before. And that I, again, like I said, I'm pretty rusty at these sorts of things, so you can understand why I didn't catch it till I actually saw it happen. I was like, wait, and I was like, oh, right, that's supposed to happen. That's the whole point of matrix math a lot of times. Anyway, so you can see in this case, I get MAX and then 0 AY, right? I get MBX here, 0 for the BY term. I get AX drops out, the N, AY, and N, BY, right? And that's no good. That's not what I wanted, right? You can see that that scale, what I wanted was M's here and here. But instead, I got M's here and here, right? Now, if I do it the other way around, now I get what I wanted, right? I get MAX, right? 0 times BX. I get NBX here, right? Then I get MAY and NBY. And that's what I actually wanted. So anyway, getting back to it, what I was saying was, in this case, you can kind of see that if I wanted to split these up, I could. Now, I have to be careful, and I was sloppy before, like I said, getting rusty, but I can split them up. I can split up a non-uniform scaled but orthogonal, so still right angle, pair of vectors. I can split them up into a scale and the unit vectors, and then I have an easier problem. So if I know that I've got A, S, P equals P prime, right? And I know that this is this one happens to be orthogonal, so A inverse equals A transpose, right? Then I can invert this much more straightforward. And it's the trick that I did before, but you can see how it's going to work, right? First, I multiply both sides by A inverse. So I get A inverse A, SP equals A inverse P prime, right? Well, what do I know about A inverse A? It's the identity matrix, so I'm just left with SP equals A inverse P prime, right? Same thing with S. So I multiply both sides by S inverse, right? And now I get P equals S inverse A inverse P prime, okay? This we already know. It's A transpose. We just said that was true. So the only problem we have is how do we compute S inverse? Well, we can use the exact same trick I used before, right? If I know that I've got some scale values, M and N, right? This is my S matrix, right? I want some matrix, I don't know what it is, right? I want something so that when I look at the terms that are produced, I get 1. Right? I get the identity matrix. 1's on the diagonal, 0's everywhere else. Well, it's not that hard to figure this out even by inspection, right? If I want this to be 1, well, this is a 0. So that means it doesn't matter what's in there, at least not for this term. So I just need to put something here that makes m equal 1. Well, I just told you what that was up there. Multiplicative inverse, right? 1 over m. Done. Okay, same difference here, right? 0 times n, right? This term falls out. What's the n? Well, it's just going to be 1 over n, right? So I know already that my term is it's just a really trivial matrix. It's just 1 over m, 1 over n, zeros and zeros, right? And you can see how that multiplies out to the 1, 1, 1, right? So when you have a scale matrix, to invert the scale matrix, you just have to invert all the diagonal elements because there's no cross terms, right? There's nothing in anywhere else. So effectively, what you could say is, in order to do this, I really just have to do this, and I'm done. And that's exactly what I did. I just did it in my head, kind of, when we were doing it. I think I explained it geometrically, but this is the actual matrix math that happened. Okay. So now we finally get to the thing that I guess we'll now have to wait till Monday for us to actually do because I am out of time, but we don't have a matrix like that. We don't have a matrix that's separable into SA. And the reason is because while the scale might be separable just fine, the A is not orthonormal, right? It's not. So since we don't have orthogonal vectors, we don't have cosine theta equals 1 or 0 in all of our terms, we can't use A inverse equals A transpose. So what we're actually going to have to do next week to fix the bug is we're actually going to have to invert the matrix for real. We have to take the A matrix and invert it. Now thankfully it's a 2 by 2 matrix. That's a really easy matrix to invert. We won't even have to use like a linear algebra assistance package or any sorts, or an iterative solver or anything like that. We'll be able to just directly do it out algebraically and it'll be fine. But that's what we actually need to do. And when we do that, I think then we will get what we need for doing our texture mapping properly. That was a lot to drop on you. So let's go ahead and go to the Q&A in case people have questions, because I realized we kind of got all the way into it there. You've got some salty dogs. What does that mean? What are salty dogs? And yeah, anyway, I guess while I'm waiting to see if there are any questions, which I don't know if there are or not, but that's, like I said, that's really basic linear algebra stuff. It gets a lot cooler. But if that sort of thing is at all interesting to you, then you will love linear algebra because there's just tons and tons and tons of that. You know, really cool. It, like, you know, especially if you've used matrices and you haven't learned really linear algebra yet, so you kind of were using them a little above your comfort level of really knowing what was going on. I mean, I at least speak from my experience 20 years ago or whenever it was at this point. It's just really rewarding to go learn how it all works, because then it's very empowering and you don't have to, they're not black boxes anymore. You can just, you know, totally get what's going on, and it just really helps, you know. So yeah. I don't know if I knew or not that we would have to do reverse mapping. I probably I mean, that we would have to do skew vector reverse mapping. I suspect that I probably said something like, we aren't really going to be skewing things, so we won't have to do this. I probably even said that on the stream. But hey, we ended up skewing them. So it's not a big deal. It's really... I probably should have just inverted the matrix, but sometimes on Handmade here I avoid doing certain math things so that we don't have to get into them at inappropriate times. Because, it is an educational stream, so if I can do something using only tools that we've already learned, and I don't feel like it's a good time to really attack a particular topic, then I don't typically go into it. Oh yeah, my elbow is it's actually fine. It's just one of the things that happens usually when you're rock climbing is it's really easy to accidentally scrape some skin and have it be a little bloody, especially on like the elbow or other places where there's not a lot of fat there. It's like it's not really cushioned, it's just like right against the bone. And so a lot of times when you're climbing, especially if you screw up or or aren't paying enough attention about what you're doing, you'll scrape something. And so it was a little bloody, so I had to kind of stick a gauze on it, so I didn't want to blood stain anything. But it's not bad. It's just it's just abraded. So it looks like we don't have any questions, so that's good. So everyone just understands it all. If I gave a basic matrix math quiz, everyone will pass. Everyone will pass with flying colors. Lord Marshall, other than transpose, do you need much more from linear? From linear algebra? Yeah, I mean, so I guess what I would say is like linear algebra and also geometric algebra, if you want to be like with the cool kids now. Both of them, there's, I don't know, hundreds of valuable things you can learn for game programming in them. I mean, there's just... Linear algebra is almost, in some sense, a field created entirely for solving things on computers. Like, I mean, that's not really true, but it's kind of that way. It's like, basically, solving giant numerical problems is specifically what linear algebra was made for. And so, when you're a computer programmer, it's hard to imagine not finding useful things studying linear algebra. Like, pretty much, I mean everything. Like, the people who won the Netflix prize, right? The thing for trying to figure out what people will rate a Netflix movie given a database of prior ratings, right, is tons of linear algebra. The singular value decomposition turned out to be a very important part of solving the Netflix prize, if I remember correctly. So it's not even games, it's not even graphics, it's everything. Like, if you have problems on a computer that involve, more than one or two variables, linear algebra, right? So compression, statistics, large data mining, it's all linear algebra. Like, not all linear algebra, like that's all you need. It's like, but the underpinnings are all, you need linear algebra always. So it's really hard to, it would be really hard to study too much linear algebra. Like, it's all really very useful. Marshall, we had one example from my linear algebra book class in the book that used computers. Was surprised to see it in there. Yeah, I wish math classes taught math with computers a little more, probably, but, you know. I mean, like everything else, linear algebra is conceptual, so you're trying to learn the conceptual parts. The solving of it is not that interesting, right? It's the understanding what the actual steps are that you can use. And then, you know, solving matrices by hand is a complete waste of time, right? And hopefully math classes have gotten past ever doing that, because no scientist that I know ever solves their matrices by hand anymore. Right? You know, once you know how to work it all, you've worked it out all symbolically, and then the computer does the work. And yeah, I would agree with Sean McGrath on the fact that math papers should be published with C source code. I always find that code is clearer than math, usually. I feel like a lot of times people have to torture stuff to put it into math form. But have I seen Gilbert Strang's lectures on linear algebra? I have seen some. I watched like a couple of his intro to linear algebra ones just because I learned linear algebra from his book. His intro to linear algebra book. So I just thought it was fun to see. I wanted to see what he sounded like or whatever. But I haven't really watched any appreciable amount of them. I just kind of like watched the first one or two just to see. Ugh. Delicious. You suggest students not knowing how to solve linear algebra problems by hand. Well, let me be clear what I mean on that, because I guess that could be taken two different ways. What I mean is, I don't think you should be numerically solving linear algebra problems, right? I mean, you should know how you might do that, but doing it is a complete waste of your time, right? That's what a computer is for. What you do want to know how to be able to do by hand is the sort of stuff that I'm doing here, right? You want to know how to be able to manipulate symbolically things so that you can solve equations that you need to solve. But once you've done it, like once you've said, oh, this is going to be an A inverse here, and I know that it's not orthonormal, so I need a real inverse, and blah, blah, blah. Don't invert the matrix yourself, because you can just ask Mathematica to invert the matrix for you, and then you won't make any mistakes, right? So, I don't think students should be sitting around doing menial math chores. If there isn't a conceptual point to it, then it just seems wrong to me. Because what are they gaining, Jesse Meyer, would you consider using C++ templates for matrices, say in 3D programming? In 3D programming, it's usually not necessary because there aren't that many permutations of what you want to do. So typically the argument for doing something with templates is if you have a lot more, like if you were doing more types of sizes. So let's say that you weren't doing 3D programming, you just had like a bunch of different matrix sizes, 4x3, 10x10, 6x9, whatever. Maybe then it makes some sense. I don't really like templates because they're super janky and bad. So I tend not to use them. But if you don't mind the jankiness, then, then that's what they're made for, so they if you can put up with the jank. All right, looks like we are done. All right, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org. It comes with a source code so you can play around with it. And over the weekend, if you want, now that I've explained exactly what you need to do to fix the bug, you could try fixing the bug yourself. See how you do. All right, we also have a forum site you can go to if you want to ask questions. We have a Patreon page to go to if you want to support the video series. We have a schedule bot that you can use to find out when we're going to be live. And we have an episode guide, and that episode guide can teach you things about the past. Anything that you've missed on Handmade Hero, you can get there. That's about it for today. I will be back probably next week sometime. I don't know. I haven't posted the schedule yet. Take a look at that schedule bot if you want to know. Until then, have fun programming, have a good weekend, and I'll see you guys on the internet. Take it easy, everyone.